Hello and good morning, everyone. My name is Amir Reza Nadiripur, and I am from the Institute of High Voltage and High Current, the School of Electrical Engineering, Faculty of Engineering, University Technology, Malaysia. Today, I would like to warmly invite you to Distinguished Lecture Series number 106, brought to you from Live Faculty of Engineering, University Technology, Malaysia. First of all, I would like to thank Professor Datu Engineer Dr. Muhammad Rafiq, our Dean of the Faculty of Engineering, for excellent organizing this lecture. For your information, distinguished lecture series, we invited prominent professors around the world to share the knowledge, expertise, and experience, and I am sure to exchange ideas. Therefore, it gives me great pleasure to invite our speaker today, Professor Pierluigi Mancarella from the University of Melbourne in Australia. Prof. Mancarella will deliver the lecture entitled Community Energy Systems, Microgrid, and the Energy Quadrilateral. For those who know, Prof. Pierluigi is a well-known professor in the field of the microgrid and smart grids energy systems. Without any delay, I would like to invite Professor Muhammad Rafiq, the Dean of the Faculty of Engineering, for further introduction of our speaker. Over to you, Prof.
Thank you, Dr. Amir Reza. Assalamualaikum warahmatullahi wabarakatuh. Welcome everyone to our 106th UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq and I am the Dean of Engineering, University Technology, Malaysia. Today, it is my utmost pleasure to welcome Professor Pierluigi Mancarella from University of Melbourne, Australia. A bit about our distinguished speaker today. Pierluigi Mancarella is Chair Professor of Electrical Power Systems at the University of Melbourne, Australia, and Professor of Smart Energy Systems at the University of Manchester, United Kingdom. He received his MSc and PhD in Power Systems from the Politecnico di Torino, Italy, before working as a postdoc researcher at Imperial College London, UK. Pierluigi has also held visiting positions at NREL USA, Tsinghua University, China, Ecole Centrale de Lille, France, NTNU, Norway, and Universidad de Chile, Chile. His research interests include techno-economic modeling of integrated multi-energy systems, security, reliability, and resilience of future networks, grid integration of renewables and low-carbon technologies, and energy infrastructure planning under uncertainty. He has been involved in or led around 50 research projects worldwide, is author of several books and of over 300 research publications, and is an editor of the IEEE Transactions on Power Systems, IEEE Transactions on Smart Grid, and IEEE Systems Journal. Pierluigi is an IEEE Power and Energy Society Distinguished Lecturer, holds the 2017 VESCI Innovation Fellowship by the Victorian Government for his project on urban-scale virtual power plants, and is a recipient of an International Newton Prize 2018 for his work on power system resilience in Chile. So that is a brief biography of our distinguished speaker. Here now is Professor Pierluigi Mancarella from University of Melbourne, Australia, with a lecture entitled Community Energy Systems, Microgrids, and the Energy Quadrilemma. Professor Pierluigi Mancarella, over to you.
Thank you very much for the very kind introduction. So let me now share my screen and we'll start with the presentation of it's an honor really and a great pleasure, of course, to be here, to be able to share, thanks to the invitation, some of our work we did in the past years about community energy systems and microgrids that somehow are very closely linked, and how they are related to the general transformations that we're seeing in the power and energy systems. And we are quite familiar with the energy trilemma. I will mention a few aspects of what is known as the energy quadrilemma, and we'll find out together if you're not too familiar with this concept, what I mean by that. Much of this work has been carried out at the University of Manchester, in the past few years, and still there are a few ongoing projects. While there are also new initiatives that are taking place at the University of Melbourne, where I'm now leading the Power Energy Systems group. Now let's get immediately into the core of this presentation. We talk about energy systems, low carbon energy systems, and we think that somehow we found a way forward, which is integration of renewables, wind, solar. I think we've solved the problem. But what is really the problem? And if you look really in a from a holistic point of view, we know that there is a so-called energy trilemma. So the moment that you integrate renewables, then you need somehow to meet a number of criteria that got to do with, of course, aspects of decarbonization, which are prompting development of renewable energy systems in the first place. But at the same time, we want to guarantee affordability for the end users in the whole system, as well as reliability, so both security of supply and reliability of the whole energy system. And the perspective of this energy trilemma is actually different depending on where you are around the world. So, for example, if you take the perspective of modern country, modern rich country, for example, the UK. So we see that probably the main aspect of interest and concern is reliability. And we look at the energy systems it is today, who is or it used to be until 10 or 20 years ago, before this big transformation that we are witnessing, who is providing reliability in the sort of traditional system. You will see that if you sketch very synthetically the main providers of reliability and system services, effectively it's all about what flexible generation units can do in terms of power system control, provision of ancillary services to keep the security of the system, that. Of course, if you're also interconnected, you can borrow, so to speak. You can lend and borrow somehow flexibility. Now, with more and more renewables into the system, the traditional providers of flexibility, reliability, ancillary services are somehow disappearing from the system, because it was all in the hands of these conventional generators that are being displaced slowly by renewables, both at the system level and very distributed level. So what happens next? Obviously, we may end up in trouble. Like, you might end up kind of blackouts, and obviously nobody's happy when there is a blackout. And how far are we potentially from this kind of situation? Well, not too far, because effectively, just to give you an example, already seen a number of blackouts around the world in recent years. I put here the picture of the separation between South Australia and the rest of the Australian system, where there was the blackout in South Australia a few years ago that was driven by extreme weather event and some maloperation protection settings in wind turbines. With more and more renewables in the systems and difficulty in operating the grid, especially under very difficult external conditions, that we'll see more about this. Well, overall, the reliability of the system is at risk, including in very modern countries like the UK or Australia in this case. Of course, when there is a problem, as engineers, we find a solution, and there are lots of potential solutions could be found. And in fact, after South Australia blackout, there was Tesla who proposed to install this very large battery that became at the time the largest battery in the world, 100 megawatts of capacity, to help support the South Australian system managing integration of renewables and potential security issues. And these technologies are working brilliantly, and in fact demonstrate the ability of engineering to sort of develop solutions whenever there is a problem, but we did not have any doubts, of course, about that. So what we will see more and more is effectively an architectural transformation that is technology driven from a system that was operated somehow unidirectionally, where flexibility was, as I was mentioning earlier in that sketch that I showed before, flexibility moves from large-scale conventional generators to a demand side that is relatively inflexible, and then there are in between, of course, the transmission and distribution networks, transitioning towards a system where there are more and more renewables, including at the level of transmission of transmission system, and these renewables may be more inflexible because they are less capable to be controlled overall. Therefore, we will need to look for flexibility elsewhere, and naturally, this flexibility will probably come from the new energy resources that are turning up in the system, so-called distributed energy resources, DR, that we see in buildings with sort of controllable buildings, smart buildings, more and more electric vehicles in the future, and of course, battery energy storage systems typically coupled to photovoltaic panels. So in this context, what we see is that the development of more and more intelligent energy systems that are aggregated at the very distributed level, starting from really the low voltage level, so-called microgrids, but also communities, smart districts, and all that. Somehow they will start interacting with new actors in the system, so-called distribution system operator, that is replacing distribution network operator, which was relatively passive in the past. But now this new actor, distribution system operator, needs to balance all these active resources that are down the system that effectively is completely transforming from our houses, basically, giving way to a completely new system, effectively we call it digital energy, what we may call digital energy systems, really, that is profoundly distributed. So when we talk about communities and microgrids, we really mean all this aggregation of active devices that are at the level of distribution networks, including particular low voltage networks, and they may be aggregated in the form of VPP, virtual power plants. There's another very important concept, in the sense that once you intelligently aggregate this DR, for example, in community microgrids, but also commercial aggregators in general, effectively, you can start interacting with the rest of the energy system as if you were, as an aggregate, some form of equivalent power plant. So that's the idea of a virtual power plant that somehow is coming from the aggregation of these resources, and it will be able more and more to provide flexibility to the rest of the energy system, including the transmission system, where there may be more requirements for flexibility given variability and uncertainty or renewables. So it's really a fundamental bottom-up transformation where now you move from sort of unilateral direction, bottom-up, large-scale conventional generators, transmission to passive distribution, from actually a very active distribution system with all these distributed energy resources and new stakeholders, new actors, new concepts, particularly communities and microgrids. So moving forward, effectively flexibility and in general system reliability and the provision of system services to guarantee this reliability we provide from this DR in the context of these distributed energy systems, and particularly what we said, communities, microgrids, virtual power plants, and of course there would be a very tight interaction and integration of electricity with other energy vectors, energy sectors, to example, heating and cooling, particularly by electric heat pumps, transport by electric vehicles, future fuels by production of green hydrogen by electrolyzers and all that. So it's really sort of new energy system in which communities and microgrids will play a more and more important roles, because effectively all this transformation are happening at the levels of buildings where all these devices will be connected. So these new concepts will play much more important role in the future. However, if you look at this from the point of view of the community or the microgrid per se, so the aggregation of buildings and relevant distributed energy resources, of course, you can look at the energy trilemma for this distributed perspective and then say, okay, how can I develop a microgrid or a community that meets my economic requirements. So you develop somehow a business case for that. Of course, it's environmentally friendly, and then technically is well operated, can provide reliability to the customers, and can operate securely in general. Now, the bigger question, however, is to what extent these microgrids and communities more in general can actually provide also a system level support, either for system operation and market operation in general, but also at the level of networks. So once you have this fundamental transformation at the edge of the grid, where buildings are, where low voltage customers are, and so on, there is a profound impact on the whole value chain, technically and economically, commercially. So what is this impact at the level of networks where microgrids communities would be connected, and upstream, and then the whole system operation and market operation? So when you look at that, there are different ways of seeing the problem. And just to give you an example, this is taken from like a community energy system, potential microgrid that will be developing at the Fisherman's Bend campus of the University of Melbourne. This area here, it's where the new engineering campus of the University of Melbourne will be developed. And we have basically developed also feasibility study for the campus to be operated as a virtual power plant. So it will be a number of distributed energy resources, including batteries, photovoltaic systems, electric vehicles, and all that, that could actually actively interact with the rest of the system right in the middle of the city of Melbourne. So this VPP concept effectively would be like as if you have a real power plant providing energy and other services in the heart of the city. However, in reality, it's the aggregation of different resources at the community level, the campus level. So when you do this, by the way, I am putting a number of references throughout the presentation, which I will share later, so that you can have a look at all details. So when you look at that, effectively, this campus operates like a synchronous machines potential, like a real power plant. In here, you will be familiar with the PQ, active power, reactive power capability charts of a synchronous generator. So when you aggregate these resources, effectively, the campus would operate as some form of synchronous generators, but the characteristics of synchronous generator would actually change with time, because at different times of the day, effectively, the operational point of all the campus resources would change. Therefore, also the ability of providing active and reactive power to the rest of the system will change, different from, of course, a conventional power plant or a synchronous machine, where the characteristics are given depending on the characteristics of the specific machine. So it's really a fascinating concept. And what we have demonstrated is the fact that you can also provide a number of ancillary services, like a real virtual power plant would do, embed in the market to provide, for example, frequency response, frequency control ancillary services, or reactive power support to the upstream grid to provide, for example, voltage regulation besides frequency regulation. So all of these effectively is facilitating the integration of more and more resources. The system, same time developing, enabling a business case for the campus itself, because of course, the moment you participate in the market to provide system services, then you can also accrue revenue that can be used to develop new business models. From a network perspective, you can imagine, for example, that this campus could be seen as a microgrid with the potential ability to get disconnected at times if there was needed. And this is really the definition of a microgrid. So again, an aggregation of resources in a certain portion of network that, when needed, for example, when there is an upstream fault, can get disconnected from the main grid and provide reliability services to the customer inside the microgrid. So really like premium reliability services. So imagine that there is a fault in here, then the microgrid will go islanded, guaranteeing to all the stakeholders in the microgrid, or at least most of them, you might have some control disconnection to make the microgrid stable. So there would be, for all these customers here, there would be a premium reliability level, while many of the other customers will have to be disconnected. However, what is more is the fact that actually the microgrid could ideally, after the fault has been cleared and all that, could also somehow supply neighboring communities, for example. So microgrid starts also providing other kind of reliability services to nearby, not only just microgrid. Besides that, if you look at what you could, this is actually like having a big demand response scheme where the microgrid is a big flexible load that gets disconnected from system. There's also the ability to downsize the upstream grid and relying on a load disconnection the moment that there was a fault, particularly for N-1 operation where you are forced somehow to oversize the system to meet certain security criteria for system design in some countries. It may be actually very efficient to have big loads that get disconnected only when there is a fault, which is naturally relatively rare under normal conditions. So this kind of concepts, which is quite innovative in terms of system design, has already been trialed in the UK in a project called Capacity to Customers, and is really, really promising in terms of future system design, because, as I will show you in a bit, also brings, besides significant reliability value, or also economic value to different stakeholders, the networks, but also the microgrids and the communities that will be actively participating as active customers to this demand response scheme. And in fact, if you look again back to the energy trilemma, you try to think back of reliability and affordability, the two systems really go together, because we know that even before the decarbonization arrived, and so the decarbonization has created this trilemma. But even before that, power systems have always been operated and designed as a dilemma between reliability, secure supply, and affordability. There is a tension, there is a trade-off between cost and reliability. You can make a network bigger, more expensive, and improve reliability, or you can give up some reliability and the system becomes cheaper. So what's the right trade-off? The moment the new technologies such as microgrids, community energy systems allow us to develop reliability, forms of reliability support to a new system, particularly to enable a secure integration of renewable resources, we can also start looking at the affordability side of the equation. Now, when we look at that, the big question when it comes to economic planning of a system is really not so much how I deal with a given future, but actually what the future looks like in first place. Because if I know the future as an engineer, certainly I can design an optimal portfolio of resources to deliver on the best possible outcome in terms of both reliability and economics. But the problem is that the future is greatly uncertain, and it's been historically uncertain with demand in terms of demand growth. However, with more and more renewables and new technologies coming up in the system, overall, there are lots of new sources of uncertainty. So how can you plan for a future system, for a future network, when you really don't know very well the future? And of course, if different scenarios happen, for example, in this case, which is, by the way, a real model for scenarios as they were developed by Electricity Northwest, the local network operator in the area of Manchester. So if you have to decide between scenario 1, very high load growth, and scenario 5, where you have a little bit of load growth, and then the load goes down, which is, for example, what happened during the UK recession after 2008. How can you plan a system? Obviously, the design would be completely different. So in this case, the uncertainty becomes fundamental in terms of driving investment, and then becomes even more important to understand what opportunities you have to use somehow your knowledge of uncertainty, or your understanding of uncertainty. In this context, you need somehow to change your planning perspective, and what I put here is like planning for smart grid, whereby instead of going for a deterministic case and say, okay, I think I know the future, therefore, as a result, I build, for example, a transmission line or a transformer. The moment that you put yourself into an uncertain world, you develop new tools to deal with this that mathematically will be based on some form of stochastic optimization. And if you're interested in this, all the details are in these tutorial papers that we wrote some time ago with colleagues from around the world. So the moment that you embrace the fact that there is all this uncertainty in future energy systems, effectively, it is like typical stochastic tree, for example, the cost of some technology, then suddenly you would see that the results that you would get for planning would change completely. In this case, it would be a battery and so-called quadrature booster to manipulate power flows across the system. And this would allow more and more integration of renewables. So what we found effectively from a theoretical perspective is that if you want to enable really the full potential of the new technologies that are fundamentally based on control, and through them, enable more and more renewable integration, and communities and microgrids through their controllability, they allow to do all this. So if we really want to value them in future systems, we need to have a planning approach that somehow departs from traditional deterministic investment methodologies and somehow move towards more probabilistic planning for which new regulatory tools will need to be put in place. Said all of this has been already, we tested this a few years ago when I was in University of Manchester and with real implementations actually in networks around Manchester. And we saw that the ability of having communities, microgrids that could get disconnected, for example, could be a community, it could be an industrial customer, it could be a supermarket and all that, could actually greatly support the development of networks for which you will have, for example, scenarios that would be highly uncertain. And when you do this, you don't actually need to develop super complicated mathematical modeling. I mean, the philosophy may be very complicated, and the theoretical modeling is there, and I invite you to read the papers for that. However, what's interesting is actually that we did perform a very practical implementation based on a tool that is as simple as Excel to actually enable the system operator to develop their planning of their networks under uncertainty with demand-side resources based on flexible communities, flexible microgrids. And then you would basically discover that the value of having this flexibility from the demand side, from communities in particular, would, for example, move from about 35 that you might envisage under certain deterministic conditions to somehow 185. So the value is priced somehow by new methodologies as they would need it in smart systems to really enable microgrid communities and all that, maybe like 5-6 times greater than what you would think with traditional methodologies. So somehow, in order to have a smart grids developed, you also need smart methodologies to properly value assets and all that. But besides reliability, there is of course lots of discussions about a close parent of reliability, that is resilience. What is this resilience, and what is somehow planning for the most uncertain of the events? So the so-called black swans. A white swan is somehow something that you are used to, that you see all the time, so expected reliability events. But something is very, very rare that you would not expect, then we'll call this a black swan. Like if you think of the past, particularly like in the old world around Europe, there will only be white swans. So we think that the swans are all black. Then there is something really, really rare happening, like explorers go to a new world, they find Australia, and they find out that actually black swans exist too. So how do I deal with this very, very highly unexpected situation where, by the way, the low probability, a low probability event, for example, climate driven, can also have a very high impact. So there is a very big storm, there's a big flooding, wildfires and all that. They have very serious impact. So how do I deal with this kind of events? So this is what we call resilience, the ability to withstand extreme events. And somehow, if I can give you like a more proper definition taken from SIGA working group, the ability to limit the extent, severity, and duration of system degradation following an extreme event. How is this resilience different from reliability? I mean, typically you design operate the system against credible events. That's what reliability is. So there is N-1, N-2 outages. So at most, you have 1 or 2 outages at the same time in the system, and the system is designed and operated to keep going, to keep the lights on after this. But when you have a black swan, like a very big event, instead of having 1 or 2 outages, you may have like 10 outages at the same time. The system is not being designed for this. So how do you then deal with this? How do you assess, how do you quantify the impact? What metrics do you use? How do you characterize these new events? This requires a complete new thinking, complete new engineering that moves away from reliability and goes towards like this new word almost of resilience that we're seeing more and more because of the extreme events. There have been different propositions, like I will skip this, but the idea is how do we find an optimal portfolio of resources to invest in to make the system more resilient? And of course, you might be thinking that easy way of doing this is let's make the system like bigger, let's reinforce the system, let's put more networks, let's create more redundancy, which is the way that we have done until now, pretty much. Well, if you wanted to have a look at this very nice paper here by Christian Strubach a few years ago, the title, explains everything already. Why investments do not prevent blackouts. At the end of the day, putting more networks in the ground will only push the network more and more. But if something very extreme happens, perhaps having more network, having more redundancy might not be sufficient. And just to give you an example, and before doing that, I put here Kirchhoff, so the father of electrotechnics and circuit theory, against Adam Smith, the father of economics, to say that even economically, you can think of nice solutions. Effectively, the physics will always win, because, for example, you put more networks, you make right investments on that, and then suddenly you have a big storm arriving. This moves, the storm front moves across the system. It impacts in different ways, different parts of the network. Because it's very, very heavy and severe, different parts of the network fall. The network has not been designed for that. And even if you increase the redundancy, for example, of the system, eventually, if the storm is very strong, eventually will bring down the system. And in fact, what you see is that up to a certain strength, for example, the wind speed, the specific case, basically nothing happens. The system is secure, is reliable, therefore so highly resilient, where basically the loss of load frequency or the expected energy not supplied is close to zero. It seems zero, but it's not zero. It's never zero. There's always some probability of having some problem. However, the moment that the wind speed increases, then the potential impact grows exponentially, because the system effectively can cascade more and more. And then you realize that the system is losing resilience, because it's the event itself that is pushing the system to the boundaries and beyond the boundaries, of course. So how can you protect the system against such very big events? Would, for example, redundancy help? Well, what we've done is we've already demonstrated actually that's not always the case. And the right thing to do is to think in terms of another trilemma, which we call the resilience trilemma, which is, do we make the network, the system stronger? So like we upgrade the infrastructure, bigger, we add redundancy or smarter. We put more and more intelligence, and we put, for example, flexible demand, more microgrids, more intelligent communities that can support the system and themselves when there is a very big event that eventually would bring down the system in any case. And under this under this framework, we can understand that having this ability of microgrids to, for example, self-disconnect and still providing premium reliability to internal customers and customers nearby can actually provide significant benefits, significant services. I was showing you earlier how microgrids could support, for example, networks, or could support by flexibility the provision of frequency response, can also support the whole system from an adequacy perspective. So the ability of meeting the peak demand under normal conditions. In the case there was some extreme event, by aggregating these different microgrids that could be spread across the country, effectively you could facilitate significantly the ability of providing supply demand, at least local demand, even for a very long duration. In this case, again, I invite you to read these papers where there are all the details, where effectively, depending on the characteristics of the microgrid, for example, could be based on PV, can be based on combined heat and power and all that, the ability of providing capacity and therefore supply demand changes depending on for how long you need to do that. Of course, the longer you need to do this, the less capacity you can provide. But there are very nice ways and elegant ways to formally assess the contribution of these microgrids to reliability, in this case, adequacy, so planning of the system. Now, if you have to think of now both resilience and affordability, so the economics of resilience, how do you deal with extreme events in this context of uncertain future? Because this future that I'm showing here was already uncertain for normal conditions. I just don't know how the system will develop. How can I predict the black swans, the very extreme events? Effectively, it's almost impossible to do this. For example, how can you really predict an earthquake? Like, we've done lots of work in Chile with colleagues. How can you really predict an earthquake and its impact? How do you develop a methodology to deal with that? Effectively, you need a complete new methodology. There's more risk-driven rather than sort of economics-driven. And the key point, besides the mathematics of this that becomes quite more complicated, the key point is that you need to start thinking in terms of risk minimization rather than cost minimization. And basically, you need to find ways to protect yourself against these extreme events that might happen so rarely that you could not perform traditional cost-benefit analysis to assess them, basically to plan against them. So when you do that, it's very interesting to see that naturally, and we show this in several papers, naturally communities and microgrids start playing a more important role than potentially asset investments, because of their flexibility, the contribution it can provide after there is an event. So the event may bring down the system. By having very flexible communities, very flexible microgrids, to be able to restore the supply, at least locally, becomes much more important. But what else when we look, for example, at things such as an earthquake? What is the social aspect of these extreme events, social aspects of resilience? Unfortunately, there is like sort of double face. Unfortunately, there is a negative community resilience. After there is a major disruption, think of earthquakes, but also major flooding, unfortunate tsunamis, in areas that are also close to Malaysia itself. So when you have all these issues, there can be a very negative response of local people that they all panic of that. But it's also very positive at times, community resilience, where cooperation, solidarity, social networks start playing a fundamental role in terms of being able to restore energy supply. And again, the importance of communities is not just the community as a sort of physical, technical entity as we've seen so far. This is really like the social community that drives also the technical community. So it is in this context that we define more and more this idea of social resilience modeling, that is paired with the technical model resilience that we developed in the past years, and somehow we redefine the technical and the social models in a context that is really social, techno-economic perspective to plan future energy systems, looking not only at economics, not only at the reliability, but also at the resilience and the social aspects that are entailed with that. And we've done all of this in a past project. By the way, I'm very proud to share that we won the International Newton Prize 2018 for this project. It was a collaboration between the UK and Chile, indeed, to develop a strategic resilience plan for the Chilean energy system, subject to earthquakes and tsunamis. In this context, we developed this idea of social techno-economic approach to deal with all these extreme events and the ideas of communities and microgrids to facilitate all of this. Is it only for the UK? Is it only for Chile? Well, let me give you an example of Malaysia, actually, because after we did this, I was leading this project in Chile, and it was very successful. We developed this this new methodology, actually, that is now being used in Chile by the Minister of Energy and other stakeholders. Said, okay, let's prepare a new project. It was again successful. It's called TERS, Techno-Economic Framework for Resilient and Sustainable Electrification, which is actually now based on 2 case studies, one in Malaysia and one in China, and whose objective is to develop an integrated economic framework to support decision making and planning a sustainable, cost-effective, resilient somehow energy infrastructure. And let's take the case study from Malaysia, which is the area of Sarawak in Borneo Island. And what we're trying to do is try to understand in different areas of the system what is the best approach, what is the optimal techno-economic resilient design after different conditions, including the potential impact and support of the local communities. So effectively what we did in the project, these are like real pictures taken from colleagues, University of Manchester, in the project, go into Borneo, Sarawak region, talk to the communities, try to understand all the challenges that they may see in terms of electricity, in terms of affordability, in terms of design, in terms of flooding and other issues they may have. If there is a problem in the local microgrid, how they can maintain it and all that. So really a social aspect that becomes very, very intertwined with a technical aspect. And then within the project that is ongoing, we're now trying to understand, looking at, for example, a flood risk map, or modeling, for example, of landslides that can also happen in the region, how we can eventually bring together this very technical aspects of impact on infrastructure with the economic aspects that would do more with planning, with the social aspects of the communities that live there, that will be involved in the design and the operation of the system. And it's really fascinating because when we look at how you perform sustainable planning with support of these microgrids and communities, you will see that it really becomes a sort of multi-criteria optimization problem, whereby basically you may have the cost, of course, but then you need to do with normal conditions, normal impacts that we call reliability, and then you need to do with extreme impacts, that is resilience. Now indicated here the white swans and the black swans. You need different metrics to approach this, and depending on how you perform this multi-criteria analysis, the optimal design would change. So you would, for example, put the microgrids or multiple microgrids in different areas of the system, and the design itself would change. So how do you optimally do that? That's, again, part of the ongoing project, but it's really fascinating to see how this is developing. Now, you understand in this context that is therefore no longer just an energy trilemma, but effectively now it also entails social aspects, where communities and people play a key role, and that's why we talk about an energy quadrilemma, with affordability, decarbonization, reliability, with the new lens of resilience too, and finally, the social aspects. And then different places, we have different perspective. For example, in some countries like Australia, this we have to do with design of community energy systems that can be very high tech and provide system service and all that. Whereas in other areas, for example, in Sarawak, it may have more to do with how do you guarantee resilience and sustainability to isolated villages, new forms of electrification eventually. So when I look at this reminds me a lot of what happened at the dawn of power systems. When 1878, someone said, "We'll make electricity so cheap that only the rich will burn candles." And if you're wondering who said this, there was Thomas Edison that effectively built electricity from scratch at the time when it opened up Pearl Street power plant in Lower Manhattan and the distribution system to power with electricity the local community. And by the way, besides electricity, it was also powering, it was providing heat to local community because it was recovering the heat that was discarded by the engine that was used to produce electricity. When we look at this, effectively, Edison understood very well there was not only just a technical problem, it was a technical problem, an economic problem, and a social problem. The idea was how could he develop a business case for its main actually discovery, the light bulb, effectively, and then basically become rich by selling light bulbs. Well, the very first step was to convince the local people that candles were not the best thing to do, starting with the fact that they were not safe. So forget the candles, I will give you electricity. So I will give you lights, and I will also give you heat, by the way. Forget candles and fire in general. But then, so this was like social aspect and economic aspect, because again, it was driven really by the economic opportunity. Wanted to become rich was really like building a business model in the case. But then technically, to do that, you had to create electricity, because a light bulb was powered by electricity, but the electricity was barely in the equations of Maxwell, the experiments of Faraday, Ampere, and all that. It didn't really exist in practice. So that's why it really designed and engineered the whole system to make money by developing this business model and then sell light bulbs all around. So again, it was already a quadrilemma, if you wish, at the time, even though, of course, the environmental aspects were not there yet. But you may argue that by eliminating fire and candles, actually, it brought lots of benefits that could be associated with the quadrilemma today, because it meant less pollution, less risk of fire and all that. So it was really a big innovation. As I said, I see lots of similarities with what we are seeing today in this big energy transition, also because in this new era that we're potentially witnessing, I see, as I mentioned earlier, similar entrepreneurs that are working similar way. Also, the time Edison was faced by a competitor was called Tesla, like the real Tesla. Now we will see if our Tesla will also have some competitor like the Edison of the time, and somehow I think this is like a very very nice, like rich environment to create innovation, and I'm sure that many in the audience will be looking forward to developing something like this. Certainly, it's a good time to be involved in energy systems. And yeah, with this, I would like to stop my presentation, and I would like to thank again thank you for the invitation, and I would be very happy to answer questions now or in case later. And as I said, I will also share my slides later on. Thank you.
Thank you so much, Professor Pierluigi Mancarella, for your amazing and informative lecture. So I believe we all learned a lot from this lecture today. Let me inform all viewers from the Malaysia and Australia and around the world. You are welcome to post any relevant question. Here, I will read the question from the Facebook comment for Prof. Mancarella. So to kick us our question answer section, maybe I begin with one question from me first, Prof. Prof, actually, the base of your presentation is about the reliability and flexibility. And it is so interesting topic in the power system. I want to know in the microgrid, if we want to provide the more flexibility and of course reliability, is better to use especially just more energy storage system like the battery, or use more dispersed generation source such as photovoltaic and wind energy source.
Yeah, so well, there are technologies that do different things. Of course, you need the energy anyway, and so there must be a sort of basis potentially if you want to become at least self-sufficient to some extent. So to have some local distributed resource you can produce energy. Therefore, you would use batteries as support for that. However, if you do not want to be sort of self-sufficient and your ambition is not that of creating sort of independent microgrid, for example, but only to provide flexibility to the rest of the energy system, actually, you can only play with flexible loads and batteries, and effectively arbitrage with the rest of the system to provide this kind of services by demand response. So many communities might decide to do this, where there is just only a very small portion of local energy supply, but there is still lots of flexibility by batteries and flexible demand. This very much depends on the specific objectives of the community, I would have to say. If there is in particular some ambition of self-sufficiency, and on the other hand also on the market setup, because markets that, for example, favor demand side flexibility, like we are trying to develop, effectively might be potentially even more suitable for batteries and flexible loads without having distributed generation in there. But there is no really not just an answer to this. You really need to see the different technical context, the social context, again, what the community wants to do, and the economic context, the regulatory and market setup in a specific country.
Yeah, of course. Thank you so much. Let me to check receive any question or not. Not yet receive any question.
I think there is a question by Ron Wu.
There is a question here. Can you read the question? Is clear for you, Prof?
Yeah, please. Okay, please go ahead. Which question? Sorry. How to encourage affordable RE? Where I think if you look at countries like the UK or Australia, effectively renewables are already affordable. Most recent studies indicate that without incentives from the government actually as energy source, that they are already the cheapest or as cheap as other energy sources. So the question is not so much about renewables affordability, it's about affordability of integration of renewables into the system, for which this concept of the smart grid, the intelligence and the controls that you build into the system becomes more important. So once we have low cost technologies, how do we integrate into the current system a low cost too? So controllability and energy management system, that becomes even more important than the renewables per se. Enablers of renewables, like new technology, like enabling technologies, such as storage, becomes another important component. And finally, we need to redesign the markets and regulatory setups to really facilitate that. Because again, if you have all this intelligence, but then you can't play, because for example, there is no flexibility in the markets to play with your intelligent resources, then you can't develop a business case either for this. And because, for example, batteries that could become enablers of renewables, in turn, that this reflects onto renewable integration itself. So I think we are really at the stage where we're moving away from the cost of renewables is more and more about the cost of enabling technologies, the intelligence, and then how we create markets and regulation to accommodate this intelligence in future systems.
Thank you for your response. Let me to check. I think received the other question. Can you read it?
Yeah, what was the factor that needs to be considered when it comes to social aspects? This fantastic question. I do not have an answer. I can only because I mean this is not my area. I'm lucky enough to have fantastic teams actually in my projects that are really experts on this. And for what I'm seeing, is really about understanding the drivers for the communities, the role of the communities, what their passion is somehow, what the challenges are. And the only way to do this is to go out and talk to the communities. There is no other way. Everything else is speculation. Everything else is assumptions, hypothesis. Then when you go out, you talk to the community, suddenly you realize that their needs, what they would like to do, what they would like to have are completely different. That's really why we talk about social aspects, technical aspects, social techno, they become also economic aspects. Because unless you talk with them, you query them, and you understand what they really need, you can't develop a techno-economic sort of plan that is really suitable for the community itself. And as banal as this may sound, actually in engineering, this is very rarely, almost never done. It may become really like transformative.
Thank you. That excellent response. Received the other question.
What is the measurement parameter when we want to consider social impact in Quadrilemma? For example, economic factor, the parameter would be net present value. How about social impact? Again, that links with the previous question. It's a great question. Unfortunately, I do not have an answer. This really opens up to future research, I think, for everyone. It's like, everything has got to do with the consumer happiness in general, comfort level of the consumers and all that sort of quality of life of consumers is enabled by energy systems. We need to come up with these new parameters. Again, I don't have a metric. Think these are really under development, but I would like to invite everyone to really be thinking about it if they're interested, because I think there would be like big area of research and real world development in this respect in the future.
Mm-hmm. This is the second question from the same person.
Mm-hmm. How the reactive power is available in the VPP system, the PQ graph. Is it from the utility or customer side? Since most of the customer is only interested to inject real power. It's a great question. I really invite you to read a few papers I mentioned in the presentations, but also there are a few other papers that we published recently in terms of virtual power plants, these PQ maps, because basically we demonstrate that by operating reactive power in a flexible way on the customer side as an aggregator, as a virtual power plant, you can actually release active power. So by modulating reactive power, you can sell more active power, and therefore you can make more money by active power. On the other hand, selling reactive power, especially under extreme conditions, can also bring substantial benefits in some cases, especially if there is a risk of voltage collapse and all that. So there are substantial benefits in being able to control that, the reactive power. And the more we go towards distributed energy systems, distributed energy markets and communities, the more important this reactive power will be to actually manage the local network, particularly to provide active power too.
Thank you so much, Dr. Jastrow, for the question, and I appreciate Prof. Pierluigi for the reply. And let me to check, have any question more? Okay, maybe a lot of question after the day. Yeah, received one question from the Zainal.
How crucial is the application of blockchain technology in community microgrid systems? This is like an open question. I'm not sure we have actually ongoing projects that would answer this. It may not. It's not necessarily blockchain, by the way. It's like different types of technologies, and the kind of power ledgers and things like this. you can definitely set up a community energy system, a microgrid system without having these technologies. However, in the future, maybe these new technologies would facilitate more and more this kind of developments. But certainly it's not essential. It's not that we don't have the technology, we can't have community and microgrids, that they don't go together. Absolutely not.
Thank you so much. Receive the other section. Maybe today we have many questions. I appreciate Prof to reply to the question. You can read. I think this is the first question. He said, you already respond to this question.
I responded to this one about renewable energy. Yeah. And there was another question like similar to before, which is about peer-to-peer energy transactions. Again, there is a component, but it's not essential, because you can still operate a microgrid or community as some form of in a centralized way, and then you can allocate cost and benefits according to specific rules or more or less complex optimization. However, here, I think the main message I would like to give to everyone is, the real research is not about coming up with complex optimizations methodologies to do different things. The real word actually is, how do we facilitate all this new technology by keeping things very simple? Because only by keeping things simple, they can actually penetrate the market and real world and operators and all that. So peer-to-peer energy transactions, as before, they can facilitate the developments of this kind of community energy system microgrids, but they are not essential, because things can still be done in a relatively simple way. At least to start with, I think it will probably be most effective to do that.
Okay, thank you so much, Prof. Pierluigi. I think we have to finish this lecture, and if the viewers have the more questions, can just email later to Professor. And I believe Professor Pierluigi is happy to answer all questions. Now I give back to Prof. Rafi for closing remark. Over to you, Prof.
Thank you, Dr. Amireza, for moderating the session and for introducing Professor Pierluigi Mancarella to me. And to our distinguished speaker today, Professor Mancarella, thank you so very much. First of all, for accepting our invitation to speak at our distinguished lecture series, and for a great sharing session. It was certainly refreshing to see some of the researchers out there working in areas in Malaysia, such as Sarawak. So it is certainly interesting to see that development. And to all of you, all of our viewers worldwide, and all 300 of you, thank you so much for watching the UTM Engineering Distinguished Lecture Series. Do stay tuned, because we have many more interesting lectures for you. Until next time, bye-bye for now. Assalamu alaikum.
Thank you very much again. Thanks everyone. Bye.